Good morning to everyone. I'm Dr. Sumi MS. The topic of my today's presentation is CMOS devices from Unit 1 MOS transistor principles. On completion, the students will be able to explore the device fundamentals that govern the behavior of CMOS transistors and VLSI circuits, and also be able to differentiate between CMOS, NAND and NOR circuits. Complementary metal oxide semiconductor is the semiconductor technology that is being used in the transistors that are being manufactured into the most of today's computer microchips. In the CMOS technology, both kinds of transistors are used in a complementary way to form a current gate that forms an effective means of electrical control. That is, it comprises of both NMOS and PMOS. This complementary metal oxide semiconductors' main advantage over individual NMOS as well as bipolar transistor technology is that it has much smaller power dissipation. Unlike NMOS or BJT, a complementary MOSFET circuit has almost no static power dissipation. Power is only dissipated in case the circuit is actually switching. This allows integrating more CMOS gates on an IC rather than in NMOS or bipolar technology, resulting in much better performance. Complementary metal oxide semiconductor transistor consists of a P-channel MOS PMOS and an N-channel MOS NMOS. So this is the diagrammatic representation of a NMOS PMOS combined CMOS, which has a substrate and also a source, gate, drain along with a body, where if the body is of a p-type substrate, then the source and drain would be of n-type material, and vice versa in the case of PMOS. NMOS is built on a p-type substrate with n-type source and drain diffused in it. In this NMOS, the majority of the carriers are electrons, and when a high voltage is being applied at the gate, the NMOS will be conducting. That is, at input 1, NMOS will be switched on, and at input 0, NMOS will be switched off. Similarly, when a low voltage is applied at the gate, PMOS will be switched on. So PMOS will be switched on when input is 0, and it will be switched off when input is given as 1. And also NMOS is considered to be faster than PMOS because the electrons are having much higher mobility than holes. PMOS, P-channel MOSFET, consists of P-type source and drain diffused on a N-type substrate. The majority of the carriers are holes. When a high voltage is applied at the gate, the PMOS will not be conducting. And when a low voltage is applied at the gate, the PMOS will be conducting. That is, when 0 is applied, when 0 is the input, PMOS is considered to be in on state, and when 1 is the input, PMOS is considered to be in off state. The PMOS devices are more immune to noise when compared with NMOS devices. CMOS working principle. In CMOS technology, both N-type and P-type transistors are being combined to design the logic function. The same signal which turns on a transistor of one type is used to switch off the transistor of the other type. This characteristic allows the design of logic devices using simple switches without the need of a pull-up resistor. In CMOS logic gates, a collection of N-type MOSFETs is arranged in a pull-down network that is between the output as well as the ground, and instead of load resistance of NMOS logic gate, CMOS logic gate has a collection of P-type MOSFETs in the pull-up network between the output and the supply VDD. Thus, if both a p-type and n-type transistors have their gates connected to the same input, then the p-type MOSFET will be on when n-type MOSFET is switched off, and vice versa. The networks are arranged such that one is on and the other is off for a given input, either 0 or 1. CMOS offers relatively high speed, low power dissipation, high noise margins in both states, and will operate over a wide range of source and input voltages. The CMOS inverter. So the diagram represents a CMOS inverter. Here, input A is served at the gate for both the transistors, that is the PMOS as well as NMOS. The NMOS transistor has input from the ground and the PMOS transistor has input from the supply, and the output, when it is being observed, when a high voltage is given at input A, then the PMOS becomes a open circuit and NMOS is switched on and PMOS is switched off. Thereby the output will be pulled down to the ground. Similarly, when a low voltage is applied to the inverter, then NMOS is switched off and PMOS is switched on, so that the output becomes VDD, or the output is pulled up towards VDD, that is the circuit is being pulled up. So this is the truth table representing a CMOS inverter. CMOS NAND gate. The figure represents a 2-input complementary MOS NAND gate. It consists of two series NMOS transistors connected between output Y and ground, and two parallel PMOS transistors connected between output Y and the supply VDD. If either of the input A and B, A or B, is at logic 0, at least one of the NMOS will be off, thereby breaking the path from Y to ground. But at least one of the PMOS will be on in that case, creating a path from Y to the supply VDD. And the output will remain high in this case. And if both the transistor inputs are high, that is, then that case both of the NMOS transistors will be on and both of the PMOS transistors will be off. In this case, the output is pulled down to the ground, therefore the output remains low. So this truth table of NAND logic gate is given below. CMOS NOR gate. So the diagram represents a 2-input NOR gate where the NMOS transistors are connected in parallel to pull the output low when either input is high, and the PMOS transistors are connected in series to pull the output high when both inputs are low, as given in the following table. So this represents the truth table of a NOR logic gate. Quiz questions on CMOS devices. With necessary diagrams, explain CMOS inverter circuits. Draw the CMOS representation of both NAND and NOR circuits. Thank you.